Suppose we have a non-empty set of vectors. So A1, A2, up to some vector AS, in a vector space V. Now if the following vector equation, being a linear combination of these vectors, so we have C2A2 and so on, up to CSAS is equal to 0. So if this equation has one trivial solution, where the coefficients of those vectors are all 0, then S is a linearly independent set. Otherwise, if this equation has other solutions in addition to the trivial solution, then S is a linearly dependent set. So for example, if we had the set of unit vectors in 3 space, so writing this equation out for our case here, we have a coefficient C1 by I plus C2 by J plus C3 by the unit vector K. And that's equal to 0. So if we expand this in component form, we have C1 by the unit vector I plus C2 by the unit vector J plus C3 by the unit vector K. And that's equal to the 0 vector in 3 space. So as we can see, the only solution to this equation is C1 is 0, C2 is 0, and C3 is also 0. So given we have one trivial solution, then S is a linearly independent set. Now another example is if we have the set of polynomials being x, 1 minus x squared, and 1 plus 3x squared, in P2, being the vector space of polynomials with a degree less than or equal to 2. So if we write this equation, for this case, we have C1 by x plus the coefficient C2 by 1 minus x squared plus the coefficient C3 by 1 plus 3x squared. And you can think of these polynomials as each being a vector with one component. So for example, polynomial 1 would be the vector with the component x. So we set this here equal to 0. And now we can group the terms. So we have minus C2 plus 3C3 multiplied by x squared plus C1 by x plus C2 plus C3. And that's equal to 0. And now equating coefficients, we get one equation being minus c2 plus 3c3 is equal to 0, because there's no x squared terms on the right hand side. And for the second equation, we have c1 is 0, and our third equation is c2 plus c3 is equal to 0. So as we can see, c1 is 0, and if we add the first and third equation, we get c3 is 0, and therefore substituting c3 into one of these equations, we get c2 is 0. So therefore the set S is a linearly independent set, because we only have one trivial solution to our vector equation. Now another way we can look at linear independence is if we suppose that we have a set S of two or more vectors. So for example, A1, A2, and so on. So this set is linearly independent if no vector in S can be expressed as a linear combination of the other vectors in S. Now suppose we have two vectors in 2 space. So for example, A1 and A2, with their initial points at the origin. Now because they don't lie on the same line, then these vectors are linearly independent. So as you can imagine, we can't express A1, for example, as a linear combination of A2. Because if we multiply A2 by a scalar, then all we can do is change its length or negate it. So A2 will always remain on the same line. And this also applies to 3 space. So if the two vectors with their initial point at the origin don't lie on the same line, then they're linearly independent. Now in 3 space, suppose we have a plane at the origin that looks something like this. And suppose we have two vectors on the plane and one vector outside the plane, with their initial points at the origin. So these 3 vectors are linearly independent because they don't lie on the same plane. So suppose this vector is A1, this one is A2, and this one is A3. So if we scale A1 by some constant, it'll be on the same plane. And scaling A2 by another constant keeps it on the same plane. And now if we try to express A3 as a linear combination of vectors A1 and A2, so we have C1A1 plus C2A2, then we can see that this is not possible. Because when we sum these two vectors, then the resulting vector is still on the plane. So therefore A3 cannot be expressed as a linear combination of A1 and A2, and therefore the three vectors are linearly independent. And if we consider the set of unit vectors in 3 space, if we had vector k having components 0, 0, 1, and tried to express this as a linear combination of I and j, so we have some constant by I plus another coefficient by j. So this equation can't be satisfied because the third component here of I and j is 0. So we can't find values for constants C1 and C2 that'll satisfy this equation. Determine if the following vectors are linearly independent. So we start off with the equation being a constant multiplied by the first vector plus another constant by the second vector plus a third constant by the third vector. And that's equal to the 0 vector. So from this, we have C1 minus C2 plus 4C3. So we're taking the first component of each vector, and that's equal to 0. And our second equation is 3C1 plus 2C2 plus 3C3 is 0. And then we have 4C1 plus 5C2 minus 2C3 is 0. So we can write this as a matrix of coefficients augmented with the 0 vector on the right. So we have coefficients of 1, minus 1 and 4, 3, 2 and 3, and 4, 5, and minus 2. And now we can take the determinant of the matrix of coefficients. So let's call this matrix A. So we take 1 by the determinant of the minor, which is 2 by minus 2, minus 3 by 5, and then minus 1 by 3 by negative 2, minus 3 by 4. And then we have plus 4, 3 by 5, minus 2 by 4. So what we get is minus 19, minus 18, plus 4 by 7 is 28. So that gives minus 9. And therefore, because the determinant is not 0, then we only have one trivial solution to this homogeneous linear system, being C1 is 0, C2 equals 0, and C3 is equal to 0. And therefore these vectors are linearly independent.